Okay, so welcome back. The plan today is just to continue on with chapter one, picking up where we left off last time. I want to make sure I didn't see these folks in the meeting just a minute ago, but is Leonard Butler here or Nora Zangana? I think we might have uh, some registration details to get worked out. All right, so that was just the attendance detail that I wanted uh, to handle, and the the office hours for the class are posted now on the Blackboard site under the Zoom links tab. So these are my hours. Um, Basically every day I have at least some time that I'm available in the morning, and then these are the set hours. But if you're not able to make these for some reason, send me an email, let me know, and we can probably set something up at a time that works for both of us. So, but these are kind of the standard hours. The ones that will probably be the easiest for most of you are, I have an hour right before class time. Well, not quite right before, but 20 minutes before class time, where I'll be available. So you can pop in Monday, Wednesday, 9 to 10 a.m. With any questions. And office hours are always just drop in. You don't have to, make an appointment or a schedule or anything like that. You can just go to the Zoom link. Note that it's a separate Zoom link from class. So use the Zoom link that is specific to the office hours posted on Blackboard, but just go to that link during one of these times and I'll be in the meeting. Or if I'm not in the meeting, every once in a while, like Zoom will kind of like close itself in the background if it's been open and nothing's happened for too long. So sometimes that happens and I don't realize that it closed itself. So, um, if that happens, then join the meeting and then it'll pop up it'll send an email to me and remind me to reopen the meeting. We have two quotes of the day today because we missed Monday and I kind of blocked my classes as Monday, Tuesday, and then Wednesday, Thursday. So, so to keep everything from getting off schedule, the first quote of the day is from Horace, the Roman lyric poet. Uh, Rough translation: there is a mean in all things, too far to the right or left of which good cannot be found. So we'll get to, chapter 3, measures of center. Uh, we'll talk about means and modes and that kind of thing. But I think that this idea applies broadly in life. And the kind of second quote of the day, or maybe kind of an idea, uh, more than just a quote, is to make strategic use of the learning curve. So the learning curve kind of, I suppose there's a couple different ways to think about a learning curve, but it kind of looks a little bit like this. And the way that I like to think about the idea of a learning curve is on the horizontal axis, I have something like time or effort. And on the vertical axis, I have something like mastery or like value, or, what percentage of people I'm better than at this particular task, something like that. And I can actually see that if I put in like a fairly reasonable amount of time, I can get quite a bit of mastery in a field, right? Um, so there's the saying like, oh, this person's a jack of all trades and a master of none. Well, that's probably not great to be, but you also don't want to be so hyper specialized that you're a master of one trade and don't know anything else uh, about any of the other fields that are ancillary to that. Um, so I think part of, managing your career aspirations is being able to go broad enough. So having, some amount of mastery, a decent amount of mastery in a lot of different fields, even fields that you don't think are going to be directly related to your career, just having that breadth to bring to a career, to a project, to a team, whatever it may be. And then also being able to go deep in maybe one or two specific areas. So managing that breadth versus depth, right? You don't want to be like so hyper focused you can only do one thing, and the person who is like the best VCR repairman in the world is out of a job these days. But on the other hand, you don't want to be so broad that you're a jack of all trades and a master of none. You need to have, high level of mastery in some fields, which means you need to put a lot of time and effort to get a high level of mastery in an area, right? If you look at, to go from here to here took this amount of time or effort, but the same amount of additional time or effort has a diminishing marginal utility. There's a diminishing marginal return there. You get a less mastery uh, for your efforts after a while. And I mean, this is a bit of an oversimplification. There's some other things we could talk about, like Dunning-Kruger effect and things like that. So there are some cautions as well. Um, but I think, understanding that, if you read one book on a topic or something, you have at least, an understanding of what folks in that area are talking about and interested in. And um, and yeah, that can be a benefit. If nothing else, if you go in for an interview and you see that, whatever the person interviewing you has this little trinket on their desk and you're like, oh, I read a book about something related to that, maybe they have like a, um, you know, Greek like war helmet or like a little figurine or something on their desk and you're like, oh, I can talk to, for 30 seconds about something related to Greek history and like they might find that cool or that might, put me above somebody else in the interview process. Um, and kind of a related idea, I know there's lots of kind of related ideas here, but um, but when I think of information or what I'm going to spend my time learning, I kind of divide it into four quadrants. Uh, and one of the aspects is time constant. In other words, how fast does the value of this information decay to zero? So is it slow or fast? Is this dynamic information? Is it more static? I know that's kind of crunched together, but so there's some information that you learn it and a week later it's pretty much worthless. So things like you watch the sports game and there was this cool play and you can talk about it with your friends at the water cooler like for the next couple of days, but if you bring up that cool play 2 months later, they're like, what are you talking about, um, so that's kind of fast time constant versus slow time constant, things like, learning a mathematical theorem or a concept in statistics. Um, you learn that theorem and it's going to be the same theorem, the same structure a year later, 10 years later. Um, and that's not to say that, one is necessarily better than the other. There's lots of folks who work in IT and they really enjoy the challenge of kind of keeping up, right? That they're the ones who spend a lot of time keeping abreast of all the new changes. And then when somebody can't figure out, wait, this thing changed, how do I, manage this? Then they're the resource that people come to. So there's value in both sides. And then also trivial versus foundational. So can I build off of this piece of information? Can I, at the very least, connect it to a lot of other pieces of information, or can I maybe take this piece of information as a jumping off point to something more complex or more advanced? Um, if I can, that's more foundational. If I can, if it's just kind of its own little island of piece of information out there, that's kind of more trivial. So you probably can guess that I kind of like uh, slow time constant static foundational knowledge. So that's more like, math. So that's kind of where I lean, but that's not to say that that's the only uh, valuable area, and I tend to shy away from trivial and dynamic. So I don't watch a whole lot of sports, that kind of thing. Um, because whatever I learn about, watching this game or whatever, um, that information isn't valuable for very long and I can't really connect it to a whole lot else. But that's just my preference. And there are people who find value in all of these quadrants, um, and who find careers working in all these quadrants. But I think a nice way to think about, what am I learning? And, maybe maybe I don't want to spend too much of my time and effort in especially the kind of fast time constant side of things because I'm always kind of spinning my wheels unless I'm doing that for a very specific purpose, like I'm going into tech and that's the kind of career that I'm interested in. And I know that going into it, and I'm okay with that. So, all right. So that those are the thoughts for today. A little longer than usual because there were two of them because we're kind of covering Monday's missed class today. All right. So then we are going to continue with the chapter 1 PowerPoint. And we left off talking about measurement scales. And I kind of took the variables that we had mentioned last time and typed them out so they're a little nicer here. And I think I also added in a couple others. So I supplemented with a couple others. Are there any thoughts or questions before we start back into chapter 1? All right, let me switch my screen around here. Give me a minute to switch my screen and get the PowerPoint and all that up. Oh, and before I bring up the PowerPoint, I did want to point out one more thing. So let me switch my screen again. In our Blackboard site, I made available this folder, supplemental material. It'll have quite a bit of information on it in it by the end of the semester, but right now we have two pieces of information, PowerPoint presentations. You can see chapter 1 is here. There's a couple things we might reference in today's lecture, and then the chapter 2 PowerPoint is also available. And there's a couple Excel files available too for chapter 2. So, but this PowerPoint that we'll be talking about today is here in the chapter 1 PowerPoint presentations folder. All right. But when I say in the future that I'll post something, in the supplemental material folder on Blackboard, that's where it'll be. So that'll be kind of the clearinghouse for a lot of our things like PowerPoint presentations or Excel files that we might use in class or things like that, things related to the exam. Okay, so I hope you all can see my my full screen now with the PowerPoint slides on the left and my OneNote pad on the right here. So we had just finished talking about variables, specifically qualitative variables. They're distinct. They can be placed into categories. So things like a major or a degree, like are you in the business major? Are you in the chemistry major? You can't be like kind of in some major that's like between business and chemistry. You're either business or chemistry. And there's also, say, no natural order or ranking. I mean, we might choose to say order them alphabetically or order them according to like um, what division they're in or something like that. But there's not a natural ordering to them. There's not a natural reason that like business should come before chemistry that has to do with that major or that degree or some fundamental characteristic. If we put them in an order, it's basically just an arbitrary order that we choose. Or same thing with like um, the city that you live in, or same thing with even something like a zip code, right? I mean, it's numerical, but it's really just kind of a numerical descriptor for a geographic area. Oh, and I think we had also said color last time too. So let me write that down here. So in most cases, color is going to be also qualitative. And again, if you're a physicist studying lasers or something, maybe color means something more quantitative to you. But, if we're just looking at colors of people's shirts or something as a fashion designer, that is going to be qualitative. quantitative variables, these tend to be numerical and they have a natural ordering or ranking. So something like, age or height, something like number of students in a class, or first, second, third place finish, gold, silver, bronze, something like that. Um, Even something like a Likert scale that somebody mentioned last time, even though it's not, directly numerical, it has a natural ordering or ranking. There's a natural ordering to it. So we could imagine, instead of just saying strongly agree, agree, moderately agree or something like that, we could just put numbers on those for how much or how strongly somebody agrees with it. And quantitatively broke into discrete versus continuous. And a lot of folks look at these words and they think, oh, maybe continuous means that I'm like continuing to collect data or something after the fact, but that's not really what we mean here. The question is basically, if we have a more accurate measuring device, can we get more decimal places of accuracy in our measurement? If I look at something like, say, number of cars sold, or if I look at, number of students in a classroom or something like that, or if I look at a letter grade, A, B, C, D, F, these are discrete because if this salesman sold 3 cars this week, well, it's not like if I had a better sale measure, he actually sold like 3.125 cars this week. No, he sold 3 cars this week. If I just said over these 7 days, how many cars were sold by this person? 3. It doesn't, it's not that if I measure more accurately, I'm going to get more decimal places of accuracy. However, if I think of something like a person's height, well, I say, oh, they're about 5'10". Well, of course, if I had a more accurate measuring device, I could say, well, they're about 5 feet and 10.13 inches tall, or more accurate still, 10.13, 479 inches tall. So with a more accurate measuring device, and perhaps even a more accurate definition of what I mean by the variable in the first place, I can get more decimal places of accuracy. So essentially, continuous variables are ones that must be rounded, and we just accept the fact that they must be rounded. And quite often, we're making this distinction between continuous and discrete variables because we want to model them in different ways, right? If I want to make a histogram, a bar chart or a column chart, a histogram, one of those things that we've all seen that, looks a little bit like this. So this kind of a thing. If I want to make a histogram, I have to decide what my bins, so to speak, are going to be. When I start collecting the data and organizing the data, I have to say, okay, like this bar here is going to represent some chunk of the data. If it's a discrete variable like number of cars sold, they might just represent the data points themselves. 1 car sold, 2 cars sold, 3 cars sold, 4 cars sold. How many of my salespeople sold 1 car this past week? How many of my people sold 2 cars this past week? And so on. Maybe that's good enough for me uh, to make, say, a nice graphical representation like this, treating that discrete variable just kind of directly in this histogram. But something like height, if I'm measuring people's heights, I have to group some of these heights together. I have to say I'm going to group together all the heights between 5'10" exactly and 5'11" exactly into one bin and count those people. And then I have things like, if I were to look at, say, annual salary, well, I mean, maybe if we want to be really pedantic, we could argue it's discrete because you can't change it by more than 1 cent, right? You're going to pay a person a certain amount in each paycheck for 12 months. And you look at that and add them all up, and it can't go more than 2 decimal places. It can't go more refined than a penny. But on the other hand, if somebody's making, say, around $50,000, well, 1 penny is like 7 decimal places over from the leading digit. do we really care? Is somebody going to be really excited that they got a raise of a penny, or really distraught that they were shorted a penny on their salary? Probably not. We probably don't care about anything at that level. Or another way of thinking about it is, if I was looking at, the salaries of 100 people across an organization, am I going to have a histogram that's like who gets paid 1 cent, 2 cents, all the way out to like $50,000 and 1 cent, 50,000 and 2 cents? Am I going to want that level of fineness? Well, no, of course not. I'm just going to have a bunch of empty space and then one blip, and then a bunch more empty space and then another blip. That's not helpful at all. I'm going to treat salary more like a continuous variable, because I'm going to have to group together a lot of people's salaries for each of these bins, each of these columns. Right. So I mentioned last time that one of the struggles that some folks have in statistics is it's a little unlike your typical math course, because most math courses have very rigid definitions that mean very specific things, and there's always, exactly one answer that's the right answer. Some of this stuff in statistics is a little fuzzier, right? So we could make an argument for salary being a continuous variable or a discrete variable. Um, right? So some of these things, or like revenue, for instance, is another one, could be continuous, could be discrete, depending on our perspective. There's a lot more gray area in stats. And in stats, we often talk about evidence in favor of a certain idea versus evidence against a certain idea. Um, Rather than saying, we've proven this thing, which is what we would say in math, under this structure that we've created, this has to be true. We would say maybe something like we've given statistically significant evidence in favor of a certain idea. Okay. And I would actually say that SAT score or IQ, we could think of as discrete or continuous for basically the same reasons I just discussed. So that was a quick rehashing of what we talked about at the end of last class, came up with all these variables, sorted them into qualitative versus quantitative. And now we're going to take a look at the data that can come out of these variables. We're going to look at 4 different measurement scales and a little bit of a preview. The 4 scales are going to be nominal, ordinal, interval, and ratio. And these scales, nominal, ordinal, interval, and ratio, um, as we go down the line, they're going to be describing data that has more and more underlying mathematical structure to it. Data where we can do more and more computational things to that data in a sensible manner. So that's really what we're interested in here with these measurement scales. So I would say, kind of roughly speaking, this qualitative versus quantitative, continuous versus discrete, maybe is a little more relevant to say maybe the chapter 2 material coming up. And these measurement scales ideas are maybe a little more relevant to, say, the chapter 3 material coming up. That's a little bit of an oversimplification, but maybe we can roughly think of it that way. But I want to point out the idea that we're not just doing this for no reason, or we're not just talking about the different types of variables and measurement scales just to talk about it. These actually will impact how we might choose to model certain um, well, let me say how it'll impact what descriptive statistics we might choose in order to model certain phenomena later on. So we're going to come up with lots of descriptive statistics in chapters 2 and 3. And why should I use this one over that one, or this strategy over that strategy for a certain variable or for certain data? This is really going to help us sort that out. Okay, so measurement scales. The nominal measurement scale, nominal, sounds kind of like name, like we just given names to things. It classifies data into mutually exclusive categories with no natural ordering or ranking. Well, that sounds an awful lot like qualitative. So out of qualitative variables, we get nominal data. These, are essentially a one-to-one correspondence. No natural ordering or ranking on the data. If I look at 25 different people's shirt colors as they walk past me and note it down, there's no, for that data, red, blue, green, there's no natural ordering or ranking that I can impose. So next up is ordinal. The word ordinal sounds a little bit like order. So here we have data that's organized into categories, and these can be ranked. So we have a little more mathematical structure. We have the idea of less than. We have the idea of an ordering, right? Of kind of like a left and a right, or a lesser and a greater. So we're now over here in quantitative. I'm going to jump over to quantitative and get qualitative off the screen so I have a little more area over here to write. Our nominal basically goes with those qualitative variables. But ordinal, here I'm looking at data that is organized into categories with a ranking. However, differences in the sense of subtraction aren't meaningful. So if I think, for instance, of something like the place finish, first, second, third, gold, silver, bronze, something like that, I think this would be kind of the classic ordinal ranking system. First place did better than second place, right? If this was a race or whatever it may be, like first place did better than second, second did better than third. There's an ordering there, there's a ranking there. First place finished the race more quickly than second place, who finished it more quickly than third, and so on. But differences in the sense that from first place to second place is 1 unit difference, 2 minus 1, and second to third is 1 unit difference, 3 minus 2. Did first place finish faster than second place to the same extent that second finished faster than third? Well, no, it's not like, first place was 10 seconds ahead of second, who was 10 seconds ahead of third, who was 10 seconds ahead of fourth. Maybe first, second, third were all like neck and neck, and then fourth was like 30 seconds behind them, and fifth, sixth, and seventh were 30 seconds behind fourth, all pretty close together, right? So just knowing the relative place finishes doesn't really tell me how much faster they ran the race, for instance. So knowing that somebody finished one place ahead of the next person, another person, doesn't tell me much about how much quickly how much quicker they ran the race. Then our next two are interval and ratio. So interval, again, we're building up more structure here. So this has a ranking. It has a natural ordering ranking, not just an arbitrarily imposed one. Meaningful differences do exist. So now subtraction makes sense. Subtraction between our data makes sense. However, there's no meaningful zero. And this might be a little confusing. What do we mean by there no meaningful zero? Let's contrast this against ratio that has the most structure. So ratio data possesses all the characteristics of interval. That is, it has a natural ordering and ranking. Differences in the sense of subtraction between the data points do make sense. And there's also a true zero. And this little addendum in ratio, I think, is helpful. True ratios exist. In ratio data, ratios make sense. Fractions make sense. In other words, if I think of something like height, well, if I say that one person is 6 feet tall and another person is 3 feet tall, well, the person who's 6 feet tall, their measurement 6 versus the other person's measurement 3, the measurements, one is twice the other. And I would also say the person who's 6 feet tall is twice as tall as the other person. That might seem like, yeah, I mean, obviously, isn't that always the case? But it's not necessarily always the case. So height is ratio data. because if somebody measures twice as tall, if their height measurement is twice somebody else's, then they're twice as tall as that person. It also has a true zero because if I had maybe not a person, but like a board or something like that that was like zero height, it has no height. The zero is meaningful. If the measurement is zero, there's none of that thing. Again, you might say, well, isn't this always the case? Well, I mean, given that school was pushed remote today because of temperature, let's think about temperature in, say, degrees Fahrenheit. Is it true that a day that's 60 degrees Fahrenheit versus a day that's 30 degrees Fahrenheit? I mean, the measurement, 60 versus 30, one number is twice the other. But is the 60-degree day like twice as warm as the 30-degree day, or is the 80-degree day twice as warm as the 40-degree day? That doesn't really make sense to say. So if I look at the ratio of the measurements, that doesn't correspond to some ratio of the underlying thing. Or another way of looking at it is, well, if I go outside and take a measurement, and I might be able to do this today, take a measurement and I get 0 degrees Fahrenheit. Well, if I measure 0 degrees Fahrenheit, does that mean there's like no temperature? Well, no, right? So if we're measuring, say, degrees Fahrenheit, or for that matter, degrees Celsius, that's not going to be ratio. That's going to be interval. Now, if I go up 1 degree, whether Fahrenheit or Celsius, that means the same thing, whether I go from 32 to 33 or 100 to 101, it means the same thing. So differences exist. A 1 degree difference, whether I say we went from, 30 degrees as the low to 40 degrees as the high, a 10-degree difference over the day. Or if we went from 70 degrees as the low to 80 degrees as the high, that 10-degree difference means the same thing. It means the same relative change in temperature uh, in either case. So differences, subtractions make sense, but divisions essentially do not make sense, or there's not a meaningful zero. So we don't make it to ratio, but we do have interval data here. So a quick question for the science folks. Oh, as an aside, I don't have chat up when I'm in full screen like this, just because it would be covering up something and you wouldn't be able to see something that I have on the screen. So I did actually try running two screens for a while and found that it was just too distracting. So I just back down to one screen. So for my science folks, we talked about two temperature scales, degrees Fahrenheit, degrees Celsius, that are interval scales, but not ratio. Is there a ratio temperature scale?
No, it's I remembered exactly what I was going to say, and then I lost it. No, because a negative temperature would denote a lack of energy rather than
Yeah, so yeah,
uh
you're on the right track. So we could get negative degrees Fahrenheit or negative degrees Celsius. What's the scale they use in a lot of science classes, named after Lord somebody?
Kelvin.
Yeah, Kelvin. So if we look at kelvins, which is not degrees Kelvin, it's just kelvins. That's just what it is. Like if it's, 170 Kelvin, that's what it is. That actually is ratio. And I mean, don't argue this with some quantum physicist, but roughly speaking, 0 Kelvin means there is no uh, kinetic energy from the wiggling of the particles. It's absolute zero, right? Essentially, what temperature measures is the little particles, like how much are they wiggling around, how much are they jostling around. The more all these little particles in the air are jostling around, the higher the temperature is, the more kind of somehow like internal kinetic energy they have. That's a really bad, description of temperature. So don't tell Professor Farina that I've characterized temperature that way. Um, but thermodynamics is a super messy field. Um, but yeah, so roughly speaking, kind of 0 Kelvin means there is like zero heat energy. Kelvin actually is a ratio scale. So if I say one thing measures at 100 Kelvin, another thing measures at 200 Kelvin. The measurements, one is twice the other. And actually, like the heat energy that's implicit in these things, one has like twice the heat energy of the other. But that doesn't happen for degrees Fahrenheit or degrees Celsius. You can't get, at least roughly speaking, negative absolute temperature, negative Kelvin temperature. Um, Again, if you want to, see some really cool ideas, you can look, what is that called? It's the physics equivalent of number on YouTube. I think it's 60 symbols. But you can look up Professor Moriarty. That's actually his name, Professor Moriarty, like the Sherlock Holmes villain. Really cool physics professor. There is a video, or maybe a couple videos on him talking about negative absolute temperature. Really a cool idea. Negative absolute temperature is in some sense like really hot. Um, so if you're interested in that kind of stuff, you can look that up. But that's a very strange niche example. So but roughly speaking, you can't get negative Kelvin, and 0 Kelvin is a true zero. It means there's no heat energy, and that's the thing that we're kind of interested in when measuring temperature. So why do the chemists and the physicists and all those like really want you to use Kelvin, even though it's super annoying that like normal temperatures are like hundreds of degrees, or I almost said hundreds of degrees Kelvin, but normal temperatures are like hundreds of Kelvins. Well, it's because it's a ratio system. It has more structure, so you can do more things more naturally with it. Uh, so like, what is degrees Celsius? Well, 0 Celsius is just the temperature that water freezes at. I mean, it's kind of nice for us because you know, that's kind of like a number that is within the range of possibilities for us to live in. Same with Fahrenheit, right? Like 0 Fahrenheit, 50 degrees Fahrenheit, like the numbers that we use to describe, say 0 to 100 Fahrenheit or 0 to 100 Celsius are numbers that we encounter daily, maybe by walking outside or maybe by like cooking something on the stove or something like that. Um, but it's kind of annoying to have to describe something as like whatever 300 something Kelvin. Um, so degrees Fahrenheit and Celsius convenient for communication to know like should I wear a coat or flip-flops outside. Kelvin much nicer when we want to take ratios of things. Interesting little tidbit about the Celsius or centigrade scale. When it was originally conceived, 0 was boiling water and 100 was freezing water. And then when they realized that like, because you think like they just knew that there was this idea of cold and this idea of hot, and but they didn't know which way the energy necessarily went or whatever. And once they kind of aligned everything to the idea of energy and so on, they kind of realized that, okay, we should flip that around. So then it got flipped around. Okay, so we have, again, nominal, which is basically just the data that comes out of qualitative variables. Ordinal, where there's a natural ordering or ranking, but subtraction doesn't make sense. Interval, where subtraction makes sense. An increase of 1 degree Celsius is the amount of energy that it takes to raise, let me see if I get this right, 1 cc of water by, um, wait, what is it? All right, I've got to, no, 1 calorie is the amount of energy that it takes to raise 1 cc of water by 1 degree Celsius. So if you have a definition for calorie and energy and um, cubic centimeter of water, then you can work out what 1 degree Celsius is um, across the temperature scale. And ratio, ratio data having the most structure, we can take ratios of things that has a true zero. So something like number of cars sold, for instance, meaningful differences exist if one person sold 3 cars versus somebody else's 2 cars, and somebody else sold 4 cars versus somebody's 3 cars. Each one of them sold one more than their counterpart. That's a meaningful difference. Ratios also are sensible. If somebody sold 4 cars and somebody else 2 cars, the person who sold 4 measures twice as much and they did sell twice as many cars. Or if somebody sold 0 cars this month, they didn't sell any cars. It has a true zero. That's ratio data. Does anybody else want to pick a variable on here and say whether you think it is, well, it's not going to be nominal, but whether you think it is ordinal, interval, or ratio?
Would blood pressure be interval?
Yeah, blood pressure, to be completely honest, I'm not really sure. So they measure it in like millimeters of mercury. Um, so yeah, pressure, it's like, I mean, I suppose if the blood pressure cuff measured 0, um, if the pressure cuff measures 0, is that like, I don't know, there's the whole thing with like Korsakoff sounds and all of that. So to be completely honest, I'm not sure. Um, but if you were measuring say like pressure on a plate, right? Like you have a scale and it has, whatever, 1 square inch of area on this scale, and you put a bunch of stuff on it and you're like, what's the average pressure across the scale? If you put 5 pounds on it, 5 pounds per square inch. Pressure in general, um, I think would be ratio. So pressure in general, and the way that we would usually measure it, I think would be ratio. But I think pressure is one of those things that's so dependent on what you're talking about. And with blood pressure, your blood pressure is something that's almost more defined medically than scientifically. So it's like, you listen for like when the arteries kind of open and close at what pressure and all of that. To be completely honest, I don't know enough about it to know which one it is. Maybe I should, I don't know. Um, but it very well could be interval. It could be ratio. Um, so you picked I think probably the one that I am not actually sure about, that I would need more medical knowledge, or at least to think about it for a little while. So this is that nice gray area of statistics. Uh, there's a saying that goes something like something along the lines of like, statistics is so fun because we're the kids who get to play in everybody's backyard. Like if you know a lot about statistics, you get to kind of like, do stuff in lots of different fields, or think about things in lots of different fields. And so maybe I'm playing in somebody's backyard that I'm really not supposed to be in. I don't know. But any thoughts about a different any of the other variables, and which one it might fall under, which one the data might fall under? What about weight? That should be an easy one. Pretty similar to height, right? I think weight should be ratio. If I have 2 things that I'm measuring and one thing weighs 10 pounds, the other thing weighs 5 pounds, the weight measurement, one is twice the other. And also one thing weighs twice as much as the other thing. Age, probably also ratio, right? If something's age is like 0 years old, it kind of like has no age. It like just came into being. Or if, one thing is 4 years old and the other thing is 2 years old, whether it's a car or a person, whatever it may be, one is twice as old as the other. That would be a sensible thing to say. I think salary as well, right? If somebody got 0 salary, they made no money. That would be ratio. It has a meaningful 0. So kind of 2 different ways we can assess ratio. If it is a 0 measurement kind of tied to there being none of the thing we're measuring, or is a ratio between measurements consistent with the ratio between the thing we're measuring. Number of students in a class, probably also ratio, right? If there are 0 students enrolled in my class, there's nobody enrolled in my class. Or if I look at 2 classes and one has 20 students enrolled, one has 10 students enrolled. The first class has twice the number of enrollees as the other one. Result of a die roll, I think this would actually depend. I mean, we're getting out 1, 2, 3, 4, 5, 6, but if I just roll a die and look at the result, that doesn't actually mean anything, right? So why am I interested in that data? If it's like the number of spaces I get to move in Monopoly or something like that, I think that probably would be interval, right? Because I can't really get a zero. But I suppose, uh, if I can move 3 spaces versus 2 or 4 versus 3, I get to move one more space each time. That makes sense. But maybe I do even have more structure, right? If I get to move 6 spaces, that's probably twice as far as 3 spaces. So even though I don't really have a measurement of zero, I suppose I can kind of infer what a measurement of zero would look like, even though it doesn't come up on the die. And maybe I could actually push this all the way to ratio. But again, that would be kind of like I would probably want to tie the die roll to something, like maybe moving a certain number of spaces on a board. So a grade like A, B, C, D, F, we put this under quantitative, even though they're not really numerical, because they really do have a natural ordering and ranking. They have more structure than qualitative data. It's not just like, you know, A, B, C, D, F or 5 disjointed different ideas. If I asked everybody in class what grade would you like to get at the end, I think everybody would say A. At least I would hope everybody would say A. I hope, nobody would say if I had my choice of grade, I would pick D or something. Um, so there's certainly a natural ordering here that an A is a higher grade or a better grade or indicates something like better mastery of the course material than, say, a C or an F. So there's an ordering. I don't know if we can really say that there's interval, right? Does somebody who got an A relative to a B, did they do as much better? Is their mastery of the material is much greater as the B versus the C or the C versus the D? I mean, as far as percentages and how we measure students for A, B, C, D, they are 10 points apart. Maybe we could push this to interval, but does that actually translate all the way down through mastery as well? I think that's a very difficult question to answer. So this is probably interval, but maybe just ordinal. I think this is one of those gray areas. It's kind of fuzzy, right? This is the kind of stuff that our accreditors and our faculty and our administrators kind of debate about and think about. And, when I give you a grade at the end of the semester, what does that grade mean? What is it supposed to mean? What does it actually mean? And are those two things actually in line with one another? Um, and I think there's probably, it's probably one of those things that if you asked 10 educators, what does a grade mean? You'll probably get 11 different answers, right? Um, so yeah, I think this is maybe a difficult one. I think that it's clearly not ratio because I don't think we can really even, an A versus a C relative to an A versus a B, like, is the difference like twice as much or something? I think that's even a hard question to phrase, let alone ask, does that make sense uh, relative to, say, the amount of mastery of the material or something like that? So I don't think it's ratio, but I also don't think that it's nominal. I think it's got too much structure to be nominal. Interval or ordinal, would make the most sense. And I would be pretty hesitant to say if one person scored one grade higher than another, that that's somehow really meaningful. So I would probably stick with ordinal unless somebody could give a pretty solid argument in favor of interval. I think the most solid argument would be that, well, when you compute a percentage at the end of the semester and assign a grade to that, that's a consistent 10 percentage point difference between the grades until you get down to F, which is just kind of a catch-all. But the consistency of the 10 percentage point difference is maybe, I think, the only argument in favor of interval. And I think it's maybe not the strongest argument. Time, probably something like age. Um, Presuming we're looking at, at a time with a distinct starting point, like, you know, uh, we have a rat in a maze and we open the door and he's going to try to get the cheese and we time him. We, click the stopwatch when the door is open. So when we measure zero time, that's like the start of the experiment. That's a meaningful zero. Or if one rat took 2 minutes and another 1 minute, the one rat took twice as long as the other one to find the cheese. But again, context matters a little bit. If we're talking about like, the year, like 2025, I mean, zero, if I measure zero time at zero AD or zero BC or whatever, that's again kind of just like an anchor, just like a flag stuck in the ground. And we say we're going to measure forward from here and backward from there. And it's a little bit like degrees Fahrenheit or degrees Celsius, right? You wouldn't say that like the year 2000 was like somehow twice as whatever, twice as removed from history or something as the year 1000. The measurements, the numbers are twice one another, but that doesn't really filter through to anything meaningful. So again, this is going to depend on context. It's going to be either interval or ratio. Something like number of stars on a rating scale. Again, I think this is questionable. I would probably go as far down as just ordinal. If you look on Amazon and you see this is, rated 4.7 stars or something. Well, something that's rated 4.7 stars is probably a better product, or at least it's an indication of a better product than, say, a 4.3. I mean, these days with the AI bots and suspicions that, the people making the products are essentially paying people to write them, good reviews, that kind of thing. Who knows? But forgetting about all of that, I think we could certainly say ordinal here, just looking at the data that more stars is more better, roughly speaking. And but interval even is a 3-star, well, let's say a 2-star to a 3-star versus a 3 to a 4-star. Is that the same, jump in quality? Uh, I'm not sure about that. I'd be pretty hesitant to apply meaning to those differences, to those subtractions, unless I had a really good, really good support to do that. But just by default, I'd be pretty hesitant to do that because I'm not really seeing that right away. That you know that one unit jump in stars means a certain unit jump in, say, quality or satisfaction or something like that. Um, okay. Yeah. And just really quickly, these last couple revenues. So like the revenue of a company, this would be ratio. If a company earns zero revenue, they earned no revenue that year. If one company earns twice the revenue of another, if the measurement is twice, uh, if the measurement of one company for another is 2 times, then one company earned twice the revenue of the other. A Likert scale, it's certainly ordinal. It has a natural ordering. Somebody who strongly agrees with a statement, agrees more than somebody who just agrees or who moderately agrees or something. But again, just kind of like the stars, I'd be really hesitant to call this interval data and start using differences, even if I did overlay like 5 is strongly agree and 4 is agree and 3 is like neutral or something. Even if I overlaid numbers, I'd be really hesitant to apply any meaning to those differences between the numbers. So one jump or 2 jumps without a lot of support. So I'd probably say ordinal here, right? And then last but not least, SAT scores or IQ test scores, things like that. These are not, this is a little bit of a challenging one because you need to know a little bit about how these are computed, but these are not computed as, like when you take an exam, if you get like half the stuff right, you get a 50% on the exam, or if you get 90% of the stuff right, you get a 90% on the exam. These aren't computed that way. They're computed basically on a scale that is normed to something uh, that the people making the test, they want a certain distribution, and they norm the test to that distribution, kind of more or less. So like, for instance, if you, at least as far as I know, unless they've changed it, if you like didn't answer a single question right on the SAT, if you got them all wrong, you would get a score of like 200 or something like that. You wouldn't get a score of 0. So there's not a meaningful 0. That means ratios aren't going to really make sense. We certainly have at least ordinal, because you'd rather have a higher SAT score than a lower, or rather have a higher IQ than a lower one. Those indicate better performance on the test. But again, do we have interval or not? Is there a meaningful difference? Is there a meaningful subtraction? Um, I don't know. I would say probably not. I would say this is probably ordinal, maybe interval. But again, I think, when I'm looking at ordinal versus interval, my kind of default feeling is that most of the time I'm going to lean toward ordinal, unless I can really make a good argument for interval. I think that's probably the hardest to decide between. Maybe that's a little bit of a cop out on my part, but I would rather not assume more structure and use a statistical technique that relies on that structure, and then have that descriptive technique really appear to say something about the data that really isn't true about the data. I'd rather avoid that and use a more conservative technique that only relies, say, on the ordering, than kind of assume too much and then make a mistake. So, maybe that's just kind of my perspective, but I would kind of, go with ordinal unless I can make a pretty clear argument for interval. And I think often it's difficult to make a clear argument for interval unless you had a lot more information about how the thing is measured, how it's going to be used, and all of that. But I think something like temperature is the best example of interval, because we all kind of understand how temperatures work, I think, even if not at the technical level, at least conceptually. All right, any questions on these? Okay, so took quite a while to get through 2 slides, but not all of the slides will take this long. I know you're probably looking at this and saying, geez, 29 slides. This is just, we're going to spend the whole semester getting through just chapter 1, but um, most of the rest of the slides until the last few are going to go pretty quickly. All right, so part of chapter 1 is a discussion of kind of experimental design. So something that we said the first day of class, basically, what's the definition of statistics? Or was it the first day or second day? Might have been the second day. But it's the process of taking raw data and putting it into a more usable form. Well, where do we get this raw data from? So where we get the raw data from, that's a discussion of experimental design. How do we collect data? We've talked a little bit about what data might look like or how we might categorize types of data, but where does the data come from? We're not going to talk very much in this course about experimental design, but we'll touch on it a little bit here in chapter 1, just as kind of an overview of the topic. But this is something that, if somebody was going into medical research or something, they would spend a lot more time on. They might even take a whole class, a whole course in this topic, but it's not really going to be the focus of our discussion here. Number one, because this is really foundationally a math course. And number two, because uh, I think the details of this depend so much on the subfield that you're in. Are you in medicine? Are you in psychology? Are you in business and finance or economics? Or so we're just scratching the surface here, hitting some of the high points. So how do we gather data? Right? I have my research question. I want to find the average height of people in Pittsburgh. I need to gather some data. Well, I could do a telephone survey. I could call people up on the phone. I could mail a questionnaire, send it to their house. I could do a personal interview. I could stop people on the street and ask them if I could measure their height, and they'll probably look at me strange. Maybe some of them will punch me or something, but maybe some of them will say, yeah, and I can measure their height and right. So these are more active types of data collection versus more passive types like surveying records. Maybe I have access to an electronic medical record, and I can, somewhere in there, in each person's chart, the doctor has put down this is the person's height, and maybe I can just go and grab all of that height data, and there's my data set for people's heights. Or maybe just observation, right? Maybe I like sit inside of a bank or something and, hopefully tell them what I'm doing so they don't like think that I'm casing the place. And as people walk out, they have the like, the how tall are you thing in case you rob the bank and try to run out the door. I don't really know how much that helps. Like I I feel like somebody like running, you're gonna be like, well, they're like, between 5 and 6 feet tall, like pretty much everybody. So anyway, I don't know if you've ever seen those things like stuck to the side of the door. I think they're probably more common in just like gas stations or something these days. But maybe I could just observe as people walk by that. I think that person's about 5'10". I think that person's about 5'7". Um, so these are more passive techniques. Or in kind of the business or finance world, like if I'm interested in say housing prices, I might go down to the real estate office and grab sale prices for houses, right? Or go to Zillow or somewhere like that that has done a lot of that work for me. I could survey records. I could, uh, that would be surveying records. Maybe I could do an observational study. So if I'm like a fashion designer and I'm interested in what's the popular color of clothing today, I might go down and just sit on a street corner and as people walk by, just tick off, oh, that person's wearing a red shirt, that one's a blue shirt, that one's a green shirt, so that I have an idea about the distribution, or well, an idea about what colors people tend to prefer. So the top ones are more active. The benefits of some of the more active collection techniques are that I can often get exactly or closer to the exact answer that I want, right? If I call somebody up and ask them like, what's your favorite color? I can get a more direct answer than, just observing somebody. Maybe they really like blue, but all their blue shirts were dirty and they haven't done laundry in 2 weeks. So the red shirt that they don't like is the only one they had to wear. Mailed questionnaire like the census, right? Uh, so something like that. Um, they're getting answers to exactly the questions they want. Or personal interview, same thing. The downsides are that the more active, uh, the more active techniques are going to be more costly, more effortful. Um, you might actually even kind of implicitly bias your results, right? If you're asking about something that people don't really want to tell the truth about, like, hey, have you ever been convicted of a crime? Uh, you know, people are going to be more hesitant to say yes to that than if you surveyed records and looked up, crime statistics that are reported, through the court systems or through the government systems. Or if you're asking, what proportion of the population has this like, disease that's not let's say an unpopular disease. Not that there are popular diseases, that's probably not the right wording, but I think you get the point, disease with, say, a stigma attached to it. Um, if you ask somebody, flat out, or if you call them on the phone, like even if they answer you at all, it's unlikely to be truthful. But if you pull the data from the EMR, that's probably going to be more accurate from the electronic medical record. So obviously, I mean, I'm saying things like, oh, just pull the data from the EMR, but that's not like, you know, your random person can't just get in there and grab your medical data. So I don't think that I'm implying that for anybody to do any research like that, they would need a very good reason to do it and work with all of the ethics folks and probably pull the data or have the data given to them in an anonymized fashion and all of that. So don't think that random goofballs are just going in and getting all of your medical data. That's not at all what I'm meaning to suggest here. But yeah, so Some pros of the more active, the first three, for instance, are you can get kind of exactly the data that you want in exactly the format that you want, or at least maybe closer to it. And the cons are it's more costly, and you might actually, by doing a more active process, you might actually bias the results, bias the data that you're getting. Speaking of bias, a statistic is biased. Remember, the statistic is the thing that we're using to kind of like estimate the population parameter. The population parameter is the thing we'd really like to know, but that's going to be too costly or difficult for us to get. So we deal with samples and we compute statistics, and we think these statistics are good estimates of parameters, hopefully. But it can be biased. A statistic can be biased if it's calculated in such a way that it's systematically different from the population parameter. So we want to start with the data collection techniques to try to make samples and therefore sample statistics that are unbiased. If we start off with kind of an inherent bias in our data, anything we do from that point forward is, it's kind of garbage in, garbage out. So we have, there's lots of sampling techniques. A couple are random sampling. This is typically the assumption that we make for all of our mathematical models. We assume random sampling. So later on, if we don't make an assumption on how the data was collected, we'll assume it was done via random sampling. Essentially, what this means is like, let's say we have 500,000 people in Pittsburgh and I want to pick 100 of them for my sample. I take every person in Pittsburgh, I assign them a number, 1, 2, 3, 4, 5 going up, and I, put all those numbers in a hat and I draw out 100 of them, and those 100 people are my sample. Now, of course, like a true random sampling almost never actually is practical. You can imagine those 100 people you choose, some of them aren't going to want to cooperate, or some of them, are going to be on vacation or something and not available or whatever it may be. So, but that would be the ideal. Systematic sampling, doing something like sample every, again, you like number all your people when you sample every 1,000 people. So you sample person number one and person 1,001 and 2,001 and 3,001, something like that. Stratified, the idea of stratified is we break the population into some different strata, some different subgroups. So for instance, I might be interested in the heights of people in Pittsburgh, but maybe I separate the men from the women, or men from women from kids, right? These are different populations, different subpopulations that are going to have different heights. So maybe I'll do a random sample in each of those and then maybe compare the heights between them. So that might be an example of creating 3 strata and then doing random sampling within them. So this is simple random sampling, which I just kind of mentioned. Something that, stats books harp on quite a bit, and I think is a fair thing to keep in the back of your mind if you haven't thought about it, is, one of maybe the more common sampling methods, just kind of generally out there, not really in peer-reviewed research, but just kind of generally speaking. And also one of the worst sampling methods is this voluntary response sample. These are the kind of things where, like, you load some news article or something, and on the side it says like, hey, what do you think about this, this policy or whatever that the mayor is, pushing or whatever, do you agree or disagree or something? So that's a voluntary response sample. Or even something, you might push it a little further and even say something like, surveys of people that, you buy a product from whatever, eBay or something, or from Amazon, and they send you an email and say, hey, rate the product, like rate your experience with this seller or whatever. That's also voluntary, right? You might do it, you might not. This is typically a poor sampling method. Why is that? Well, for one thing, you know, if I buy this product and I'm happy enough with it, I'm probably not going to rate it. If I was extremely happy with the product or the seller or something, I'm going to be more likely to rate it. And if I was extremely unhappy, I'm definitely going to rate it. I'm mad, so I'm going to give them that 1 star and write a whole screed about how terrible they are or something, but like, do you ever see that on Amazon or eBay or something? There's like a bunch of 5 star and a handful of 1 star, and there's like not really any 3 star reviews because the people who were like, yeah, I mean, you came through, you did what you said, and I'm not, blown out of the water, happy with it, but I'm not mad either. Like they just forget about it, right? Um, or if you load this news article, well, what people are reading that news article. If the news article is about the thing that the mayor is proposing, you're going to get people who are really invested in that and really strongly agree or strongly disagree. The people who really are neutral and don't really care probably didn't open the news article related to that, and they're not going to answer um, the poll either because they're not going to see it. Um, so these voluntary response samples, always take them with a really huge grain of salt, really, if you give them any credibility at all. And I typically look at them and think, okay, these are kind of the end points, right? These are like the people who feel most strongly for and against. They're probably most of the people that I'm getting here. So like if I'm looking up, I need a tradesman to do something in the house, I'm usually going to look at their 1 star reviews and see what they say. And then I'm going to look at how the company replied to the 1 star reviews. And that's going to tell me a little more than the 5 star, the 4 star reviews, or even the proportion of, the different stars, whether you're overall a 4.3 or a 4.5 star company means a lot less to me than, you know, the details of the people who were unhappy and how the company responded to the people who were unhappy. So yeah, so just be a little wary of voluntary response samples. All right, different types of studies, observational versus experimental. So an observational study, kind of as the wording suggests, the researcher observes what is happening or has happened. So this is like that example I've given a couple of times of the fashion designer sitting on the corner and just as people walk by, checking off what color shirt they're wearing. They're just observing. They're not really actively involved in the, shirt choice process or anything like that. On the other hand, we have an experimental study where the researcher is kind of manipulating the variables. The researcher is doing an experiment. They're changing one of the input variables or perhaps more and seeing how that affects an output variable. And then they change that input variable in a different way and see the effect on the output variable again in that news scenario. So we have inputs versus outputs. We have kind of an input variable. We have the experiment, this kind of black box that does something. And then we have an output. Often we call this the independent variable is the input and the dependent variable is the output. That's kind of the more maybe mathy way to say it. Let me see, let me go to the next slide here. So the independent variable, this is the one that's being changed. This is the one that the experimenter is deciding what that input's going to be. Sometimes this is called the explanatory variable, and the output would be called the response variable. So the dependent variable, sometimes called the response variable. And the example I like to use here is like medication, right? So the researcher might have some new pharmaceutical that they've come up with, some new chemical, and they're saying, okay, well, if I give 10 milligrams, does the person, get better, more quickly than I might expect or something like that? If I give 20 milligrams instead, do they get better faster or do they get better at a higher rate? If I give 30 milligrams, do they get better even faster? Or maybe I'm looking at In a different scenario, maybe if I give 10 versus 20 versus 30 milligrams, what are the side effects? Do they get more severe really quickly or more prevalent? Is it that at 30 milligrams, almost everybody has pretty significant side effects, but at 10 milligrams, very few people do. So I might be looking at, say, dosage as my input, for instance, using some different dosages, and then looking at the response of, I don't know, let's say chance of uh, successful treatment, or maybe side effects, something like that. At least for our mental model here, I think it's good to think about just one independent variable, say amount of dosage that we're giving, 10, 20, 30 milligrams, and pick, one output variable. So maybe we're looking at, you know, the chance that that treatment is successful, the chance that this drug seems to lead to a cure of that disease. We do have a couple of challenges here, though, and that is that we can have confounding variables. This is a variable that is influencing the dependent variable, the response variable, maybe influencing the chance of success of treatment, but it's not the independent variable. So it is kind of a different input into the experiment, and often we don't really explicitly know that it's there. So this is a confounding variable. And the kind of classic place to see this is maybe with medication that treats things like, say, anxiety or depression, something like that. So if somebody is feeling depressed and they go into a study, maybe they feel like there's nothing that they can do to make their life better, but they sign up for this study, they're taking a drug, and then their depression gets less severe. Well, is it the actual chemical response, the pharmaceutical response, that is causing the depression to be less severe, or is it maybe just them being part of the study, them taking this medication, them feeling like they're taking control of something and doing something to better their lives that's making their depression less severe? Is it kind of the pharmaceutical element or the behavior element that's that's seemingly increasing this chance of success? We're not really sure, right? Does anybody know what this is called? The something effect. Starts with a P.
Placebo effect.
Yeah, exactly. So this is the placebo, if I can spell placebo effect. Exactly. Yeah, so this so-called placebo effect you know, that since you know that you're being treated or suspect that you're being treated or think that somebody's doing something to help you out, the success actually increases, the chance of success actually increases. And this can be for things like psychiatric, but it can, where we can, I think, pretty clearly see the link between the two. But it can actually also pop up in areas uh, that at least, in my mind, I can not really see the link between the two, right? Like, physical symptoms and those kind of things. So, feeling like you're on the mend and that you're doing well can make you heal better and faster and so on. So this placebo effect could be related to a confounding variable. Maybe my drug's not actually doing anything at all, and it's just being in the study and feeling like they're taking control and feeling like they're being attended to and so on. Maybe that's what's, making that depression lift, for instance. So how do we get around this? How do we try to figure out if there's a confounding variable in play? Well, the answer is to stratify. Remember that stratified sampling before? So I might actually put a group in here in my experiment that's getting 0 milligrams of the drug. And then maybe another group that's getting 10, and another that's 20, and then that's 30. So I've taken my, let's say 100 participants in my trial, and I've randomly assigned 25 of them to get 0 milligrams of the active ingredient, 25 to get 10, 25, 20 milligrams, and 25 of them getting 30. So I split them into these 4 groups and I follow them along. And if I see that, maybe the 10, 20, and 30 all get better, at some chance of success. But if I see that the 0 group, the control group as we call it, gets better at about the same rate, then I don't think my drug is actually doing anything. Because the people who I gave 0 milligrams of my drug to, they're getting better at about the same rate as the people who I gave 10, 20, or 30 milligrams of my drug to. On the other hand, if I look at the control group and I see that they have, let's say, a 10% chance of success, but the people who get my drug have like a 50% chance of success, then I think my drug actually does something. I think there's definitely a confounding variable. That 10% chance of success maybe uh, is the influence from that confounding variable or variables. But I think that, marginal success going from 10% chance to 50% chance probably shows that my drug is actually doing something, is actually effective. So I want to control for these external influences, these confounding variables by making a control group. And the idea behind the control group is that they're treated to the greatest extent possible exactly the same way as everybody else. They have the same medical follow-ups. They even, let's say they need to take a pill, they get a pill that looks exactly the same as everybody else's pills, that has all of the same coatings and inactive ingredients and all of that stuff, but we just don't put the active ingredient in their pill. And ideally, even well, of course, the person themselves has to not know whether they're getting the placebo treatment, the control treatment, or the active ingredient. Otherwise, that would kind of, if they knew that they weren't getting the active ingredient versus knew that they were, that would, reintroduce the confounder. So they have to not know that. And of course, they agree in advance to the fact that they're going to receive a treatment and not know if it's the active one or not. So they have to not know for the patient, but ideally, this would be double blinded, that the people providing the treatment would also not know. We don't want the physicians interviewing them to, you know, to just have some subconscious like, okay, well, I know you're not on the active ingredient, so I'm pretty sure you're not getting better. So, you know, we don't want that to influence how they record their notes or how they even maybe how they talk to the patient. They might talk to this patient differently than that one because they know that one of them is on the drug and the other one not. Not even saying maliciously, just with that knowledge. So that's like a double-blinded trial where the patient doesn't know whether they're getting the treatment or the control, and none of the people interacting with the patient know either. I mean, it's recorded somewhere in some table somewhere, right? And later on, they match them back up. So it's not like nobody ever knows. But trying to trying to tease out the effects of the confounding variables as much as possible. All right, so what is the idea of sampling error? We talked about this a little bit already in the past. But remember, the goal in almost all cases, our goal is to answer a research question about a certain population. And in almost all cases, it's too expensive or just infeasible or impossible to get the actual answer to that actual question about the population. So I have to settle with a sample. I have to settle with a subgroup of that population and answer the question within that sample. And my hope is that the answer to the question for that sample is going to be pretty close to the answer to the question for the whole population, right? What's the average height of people in Pittsburgh? That's my question about the population of all people in Pittsburgh. I can't get that answer. It's 500,000 people I'd have to measure. Most of them are not going to cooperate, right? So I take a sample of size 100, I get the average height of that sample. And I'm kind of hoping that the average height of that sample is going to be pretty close to the answer that I would get if I was omniscient and got the actual average height of the population. But we can clearly see that I don't expect that the average height of my sample is going to be exactly the same as the average height of my population. I expect there to be some amount of error there. At this point, I'm saying I hope it's close. I mean, we're going to quantify that later, but I hope it's close. But I know that I expect that the answer that I get for the sample is going to be a little different, perhaps a lot different than the answer for the population. And that's the sampling error. The fact that I'm answering the question on the basis of the sample instead of the whole population. So that's the sampling error is the difference between the differences in subtraction, the sample statistic, and the population parameter. I really wish we had a different word for subtraction than difference uh, because difference just means something very different colloquially. Well, there you go, something different colloquially. I actually just there's a physics YouTuber that I watch. His name is Parth G, Parthg, uh, and he actually just posted a YouTube video about um, when people in science or really in any technical field are using technical terms. A lot of times our technical terms also have a colloquial meaning, and we have to make sure that it's kind of our job to make sure that those two aren't conflated when we are explaining something. So, but uh, difference here being subtraction. So sample statistic minus population parameter, that would be our sampling error. Okay, what is statistical significance? This is something we'll talk a lot about in chapter 8, but just to introduce the idea. So suppose we have two competing hypotheses. Maybe I say, okay, one hypothesis is the average height of people in Pittsburgh is, let's say, of adults. Just to be clear, when I say people, I'm talking about adults in Pittsburgh. I don't want to have to think about how tall kids are, what ages, and what proportion of the population would be kids. But so average height of adults in Pittsburgh. And let's say I have one hypothesis that it's under 5 feet tall, and another hypothesis that it's over 5 feet tall. Now, if I could query the entire population and get the actual average, I would know for certain which one is true. But I can't, again, in almost every circumstance, I can't do that. I'm stuck with a sample. I know there's going to be some sampling error. I get my sample, I compute the average. I say, okay, on the base of the sample, 100 people, the sample average height is, 5'8". And I might say, okay, well, 5'8" is taller than 5 feet. That means the hypothesis, average height in Pittsburgh bigger than 5 feet is supported, period, end of story, because 5'8" is taller than 5 feet. But really, I know that there's some sampling error there. So I might want to ask myself, okay, well, what's the chance that the actual average height of people in Pittsburgh is below 5 feet? But just by chance, just by happenstance, I happen to pick a sample with a bunch of tall people, unusually tall people, and that gave me an unusually high average. My sampling error is kind of way off to the right of, or my sampling error is very large, positive, and really the average height of people in Pittsburgh is under 5 feet tall. Well, I think we can intuitively say, well, if it's like 5'8" for the sample average versus, are we greater or less than 5 feet for the population average? I feel pretty confident, with that 8 inches difference in heights, and knowing something about the distribution of heights, people's heights don't vary by 5 feet or something like that, right? Uh, so I'd feel pretty confident saying, okay, 5'8" is so far above the 5 foot dividing line. I think it's very unlikely that I happen to get a sample with so many people who are so overly tall that it biased my data that far to the right. So I think it's very unlikely that this sample average being bigger than 5 feet happened by chance. Therefore, I'll presume the hypothesis that the average height of people in Pittsburgh is over 5 feet. Now, if instead I was looking at a hypothesis that the average height of people in Pittsburgh is greater than versus less than 5'7", and I got a sample average height of 5'8", Well, it could very likely be that I got a few people who were taller than typical, and maybe the actual average height is actually a little below 5'7", and the sampling error just pushed it a little to the right at 5'8". I'd be a lot less confident making the call uh, of 5'8", if my sample average was 5'8" versus a hypothesis of 5'7", more or less, than I would be if my sample average is 5'8" and I'm looking at 5 feet, more or less, right? And that's what we mean here. So statistical significance, is this result likely to have happened by chance? Is the result of me getting, um, you know, a sample like 5'8", sample with an average like 5'8", um, likely to have happened by chance if the true population average height is under 5 feet? No, that would be very unlikely to happen by chance. I can just tell with a gut feeling that that's the case. Where if it was 5'8" versus 5'7", I can really imagine that that could be much more likely to have happened by chance. Again, at this point, this is all very hand wavy and gut feeling, but in chapter 8, we'll put math to all of this and get precise answers. So just a quick note on correlation versus causation. Again, this is something that we'll visit in chapter 10, so near the end of the course, but just, it's an important idea in statistics and really just in kind of data literacy, that if we have two variables that seem to be related to one another somehow, maybe when I notice that one of the variables tends to be measured higher, the other variable tends to also be measured higher and vice versa. So that's more or less what we would call a correlation, that these two variables correlate, that they are associated with one another in some way. But what we don't want to do is we don't want to derive a causation from that. We don't want to say because the two variables are related, it must be true that the presence of variable A causes variable B to happen. Just knowing that there's a correlation doesn't really tell us anything causative. Um, so, for instance, there are a few standard examples. One of them is um, like inflation and teacher salaries. Like when inflation is high, teacher salary increases also tend to be high. So it must be true that teacher salary increases are causing inflation, right? Things like that. Um, so that's clearly not true. I think clearly not true. Um, Teachers don't make up a large enough proportion of the economy for, their salary increases alone to be directly influencing the overall inflation rate. There's another kind of funny example. This was a call into a radio show, and I really hope that this person was like just trolling them. But this person called in, and it's on YouTube, you can find it. And they were talking about how terrible these deer crossing signs are, especially in Pennsylvania. I'm sure you've all seen deer crossing signs. You're going through some back road, and there's a little sign that has like the deer crossing. And she's saying, I don't understand. They put all of these deer crossings in busy areas. Like the only time I see these signs are on roads that are busy. Why would they put all the deer crossings on busy roads? Why don't they put the deer crossings on slower roads so the deer don't get hit as much, right? Well, clearly it's not the deer crossing sign that is causing the deer to cross there. It's the deer crossing there that caused them to put the deer crossing sign up, right? So I really hope this person was trolling them and not suggesting that the deer look for a deer crossing sign and choose that area to cross. Um, so, but there's a lot of funny examples, and we'll talk about some other kind of funny examples when we get to the um, the discussion on correlation and regression. But just note that correlation does not imply causation. Um, there are lots of ways the two variables can be linked. All right, and I think we will stop here. We have these last few slides on misuses of stats. We'll come back to this next time. That'll wrap up our chapter 1 discussion, and then we will start into chapter 2. So there are a couple of homework sections due this weekend. So take a look at that. I think it's the first 2 sections of chapter 1, and then maybe the last section of chapter 1 is due next Sunday. Somebody asked, would you mind explaining what no meaningful zero means again? That was quite a while ago, so I hope I went through that enough times. But if you do have any other questions on that, let me know after we break for class. I'll stick around for a minute or so. All right. I will stop the recording.